Okay, so 3 more optimization examples. So let's see, the first one I had was, let's say we have a window being built, like a Norman type of window. So let's say we have a window that looks like this, where you've got like a rectangle, and then you've got like a semicircle on top. A lot of windows are like that. So it says we've got a window of this kind of shape, and it said if there are 12 meters of framing materials.
What number is this?
Just whatever.
Okay.
Yeah. Example 4. If there are 12 meters of framing materials, what must the dimensions of the window be to let in the most light? So we've got 12 meters of materials to frame the outside only. We're not going to even think about this really as being part of those framing materials. But we've got only 12 meters to frame the outside, and we want to maximize how much light we let in. So what's our primary equation here, you guys? Like if we're trying to maximize light. Area. Isn't that going to be like the area, like how much light comes through the window? So the area of this, I think we better like put some dimensions on here. So I'm going to say we've got the height of the window we're going to have to think about. And then we also have to think about this dimension, which is also the diameter. Nice. So like if you've got the radius of the circle going up something like that, how big is this? 2r. Or diameter, right? But we're just going to say radius, okay? So we said we wanted to maximize for our primary equation again what? The area covered by the window. So we're going to say the area is what? What's the area of that shape? 2RH, that covers the rectangle, and
plus
pi r squared, that's the semicircle. How many variables do we have here right now? 2. We've got r and h. So somehow we need to come up with another equation to eliminate one of those, right? So what else did they tell us that we haven't used yet? The 12 meters of material, and what's that describing, Paul?
max perimeter.
Yeah, that's like, it's not saying it's the max perimeter, they're saying use that 12. They're saying 12 equals the perimeter. The frame is going to be the perimeter, isn't it? So what's the perimeter of this thing?
It's just half circumference of the circle plus the 3 sides of the rectangle.
So half, and circumference is 2 pi r. That's this part.
So it's just
Yeah, pi r.
So pi r plus,
2h, 2r.
okay. So pi r plus 2h plus 2r equals 12. How can we use that to solve our issue over here? So I mean, in multivariable calculus, you can just do it this way.
H.
You can solve for H easily.
Which one do you guys want? We only have one h. Yeah?
Yeah.
Maybe that's going to be nicer. Let's just solve for h then. Okay. So we say 2h is 12 minus 2r minus pi r. Yeah? So divide that by 2. You've got h. So your secondary equation, the whole point of doing it is so we could get this expression so we get rid of one of our variables down here. That's the whole point. So we don't even want to do multivariable calculus even if we needed to, because it's uglier, it takes long. Okay, so now this is going to be a function of just r, so we have 2r, and then 12 minus 2r minus pi r over 2. Those 2's will cancel. That's good at least. Plus half pi r squared. Let's see if we can simplify that. No, it's not that bad. So I'm going to distribute my r. So we've got 12r minus 2r squared minus pi r squared plus half pi r squared. Oh, so we have some like terms at the end? Pi r squared things? So we could say that's -1 plus a half. That's -1/2 of those pi r squared things. So that covers those. Then we've got minus 2r squared plus 12r still. Okay, so that's a function that describes the area of that window just based on the radius. Yeah? So then the whole point of getting that function was so we could maximize it. So we're going to take the derivative. So that's the easy derivative. So the 2 is going to cancel the 1/2. So you're going to have negative pi r. 2 is going to make that a 4r. And then plus 12. Sweet. Set it to 0. So we're going to have, if I factor out r, we're going to have negative pi minus 4 equals negative 12. Just follow me? So r is negative 12 over negative pi minus 4. See what that is, please. That's the exact answer. Which, by the way, can your calculator give you that exact answer? No. No, it cannot. So put that in your calculator and see what it is about. What is it? Let's see.
1.68.
It's not about that calculation. The calculator says you calculate this here. With that, half Calc per second.
It's 1.68.
Come on, everybody, check you.
This group, so,
So Paul says 1.680. You guys remember that in this class, we're always going to round in 3 decimal places or more,
Yeah.
never less.
this is
And I didn't even tell you units, right? We should always have units. So, oh, I think I did say meters. Didn't I say meters? That was this 12. So then this is in meters. It's not square meters or anything. It's a length. It's a radius, right? And the question said this time, remember, it could have said anything. It could have said how much light. That would imply, like, what's the A value? This time it said, what are the dimensions of the window? So the window is a radius of this.
which of these play back in?
And we also need the height, right? So you plug it back in and get the H is, can you guys do that real quick and tell me what it is here? About, what is the H that's going to maximize how much light we get?
Makes it like 2.
What did you get, Brenda?
So that makes it square.
Oh, about
R
4.
equals H. You round to your.
I ran
Okay.
1.68.
So about 1.680. So then the window, what would this part of the window's dimensions be right here? Would it be square? This
Oh,
part would be, what would it really look like? It would really look like
Wide bottom.
that, wouldn't it? Here's your
You have 2 of those
1.680.
ones.
You've got 2 of them here for like 3 point what? Okay, so that's that one. Let's do another one. Let's see what else we've got. I want to do one where we have a slider. So let's see.
Oh, mental floss is the Vlog Brothers.
I think so.
Huh? I like that.
What did I know? How do they do? Where do they go?
They do a lot of science videos on YouTube. That's what mental floss. Mental floss is kind of like a. No, they just like a series of videos. I think they do a website on it too. It's really cool. We should watch it. I think they're called the Vlog Brothers.
Log?
Yeah, but you can just look at mental floss.
Because it's supposed to be a skull. That's for
He,
skull.
now he actually writes books. So
Is it
it's
like
like-
a-
Yeah.
I wonder how- Really smart guy.
Did you do it?
I'm not saying you are.
So that's your deal. Because you guys
And did you have that book?
Like
Is
that.
that so next time?
She gets.
Change it like
Okay,
Oh, that's not good.
so there's two possible questions I had here. I think I wanted to do, which one? I want to do question A. So question A says, you have a piece of wire, right? Just one piece of wire. Wes, close that. So you have one piece of wire. You're going to cut it in a certain spot, and then you're going to fold it up into a square and a circle. You could also make any other shapes and do the same kind of problem, right? So we're going to take that square, that long piece of wire, cut it, and make a circle out of one piece, make a square out of the other piece. So the goal here on this one is to find the minimum possible area enclosed when we do that. There's all kinds of variations on this problem, right? So obviously you only have so much wire, so I need to tell you how much wire, how much does it say there on A? So it says you've got an 80-foot piece. How can you find a minimum possible area? So let's see, that's the triangle one. Let's look at this one. So here's the idea. Here's the wire, you could cut it, and this is the kind of thing that could happen. So when would we get the minimum possible area? Would it be right here? Think about the area of that circle. It's quite a bit. If we use part of it for the square, and a little bit more, and then we use a little bit more of it, and a little bit more, the area enclosed by both is shrinking, is it not? You guys see that? So at the beginning, if we just use the whole wire to make a circle, it's got a decent amount of area. It's going to take a lot to fill that in. If we cut a piece off and make it into a square, and that square is going to have a little tiny bit of area, and you've still got a lot for the circle. But if we cut it like almost in half, then we've got some area for the circle and some area for the square, but how's that going to compare to the original? Think about it back at the beginning. Isn't that a lot more? Or about the same, maybe? So look at on the right there. Can you see that it's going down to a minimum? Great. It'd be tough to just guess this, wouldn't it? Like you'd have to guess a whole bunch of times. And each time you'd have to calculate what? So you'd have to add up what? You'd have to add up both areas and do pi r squared each time. That would be a pain. So the idea is that you can kind of see it. It looks like visually that the minimum occurs somewhere around, they're about the same size. Does it look like that? So I'm thinking we're going to cut that wire almost in half. We'll have to see. Okay, so that's the picture. Let's do it. I need a word so I can just retract it. That would be so nice.
Cease.
Okay, so we said we have an 80-foot piece of wire. And like I said, we're minimizing, not maximizing. So we've got a square and a circle. How are we going to do that? So yeah. So A, what variables is that going to depend on? I don't know. What do you guys want to call this length of the square? You want to call it L? I mean, we could call it anything, right?
S.
Okay, we'll
Square.
call it S. Side of the square, so that's also S. So then, what should we call this?
R.
So our function is going to have how many variables? It's going to be like R and S. So we're going to say the area of this guy is R squared, and the area of this guy is S squared. Very simple. Then we say, hey, we've got two variables. How can we somehow get rid of one of them? And the answer is pretty similar to that last one, right?
Calculus.
Oh, we found another equation. We use that 80 feet. We use 80 equals
80 is the what?
is the whole total.
It's the total perimeter, YJ.
Because that's all you have to make these shapes out of.
Outside of the
Yeah, like this is the actual wire, right? Like you have a piece of wire at the beginning, you chop it, then this piece you fold up into the circle, and this piece you bend it into the square. That's the perimeter, isn't it? Okay, so then we've got 80 for the perimeter is equal to, what's the perimeter here? Circumference.
4s.
So 2 pi r plus 4s.
I've
So then we'll solve for one. Let's see, I'm going to solve for the one I did. I solved for r.
really.
Yeah, I did. I won't do it that way. So I'm going to go 80 minus 4s over 2 pi. And then stick that in. So now we're just going to have a of r. We've got pi r squared plus, oh whoops. My bad. We've got 80 minus 4s over 2 pi squared times pi, right? Pi, my bad. Pi r squared plus s squared. And then we better try simplify that, right? So what is this? Pi, well, pi's, there's going to be 1 pi left, isn't there? So we're going to have like pi over 4 pi squared. What's going to be inside? You guys help me?
16.
Do we have to, by the way, expand that out if we don't want to? It's kind of our choice. What do you guys think? We're going to take the derivative next. Should we do it or not?
Not keep it.
Want to keep it? Let's just keep it this time and see. So that thing's squared. I squared the bottom. So we'll cancel one of the pi's, like Brenda said. So that's A. So A prime is going to be what? That 4 pi, is that a variable? So I can just put that in front, right? And then what's the derivative of the top part? 2 stuff to the 1 times derivative of the stuff plus 2s.
Because the bottom function is
Yeah, it's just a constant, right? You don't have to worry about it. Okay, and then that doesn't look too bad. We should be able to set that to 0. So let's see. So we go 0. That's going to be 1 over 2 pi from that. And then we have negative 4 on top anyway. And then we've got 80 minus 4s plus 2s. So that's really just
2 pi.
negative 2 over pi. 80 minus 4s plus 2s. Get a new marker.
Where'd your 2 go? Okay, I saw it. Nope. You simplified and then you multiplied this one. I got you.
Anybody else have a question on my simplifying? I could make a mistake, I don't know. Okay, we're setting this to 0. So we should probably collect some like terms. So we've got negative 160 over pi. And then this is going to be positive 8s over pi plus 2s. I'm going to move that to the other side. So 160 over pi equals, I'm going to factor out my s. So that's 8 over pi plus 2. Yeah. And then divide that chunk to the other side, and I'll probably just use my calculator to do it. So let's see, so we've got that s equals 160 over pi, all divided by 8 over pi plus 2. What is that? Let's see if you guys get the same thing that I had from earlier. So it looks like we only got one critical point for this, yeah? You could get more. On some of your problems, you're probably going to have a couple, and then you're going to have to go back to the original constraints of the problem and think about it. Like, for instance, if we got a critical point that told us 120, would that make sense?
No, because you only have 80.
You only have 80 feet of wire, right? So, like, it's got to be, like, between 0 and 80. So if a critical point was outside those bounds, it was a critical point, but it doesn't fit the constraints of the situation, okay? What is that number?
11.
And I think I said feet. So this is feet, right? It's a length. Sometimes it might be an area or something, so watch that. They usually give you like a 9-point for response question, 1 point is for the units.
And so that's the size of the square. You don't have the
Right.
radius.
So then I can plug it in right here to get the radius.
Okay.
So just a question. When we were looking at the visual on the diagram when I projected it, didn't it kind of look like maybe the minimum could have actually been when it was all the circle? Maybe that was less. Or all the square. Do you guys remember when I was sliding that?
Yeah.
Couldn't it have been maybe one of the endpoints on this one as well? So I think we should probably check and make sure that's actually smaller. Because it might not have been. It might have been one of the ends. Yeah. I don't know. So anyway, let's try that. So x, let's look at 0 for the one endpoint, our critical point, and this isn't really x, right? We called it s. And then let's think about the area as a function of s. So we need to check 0, we need to check our critical point. What's the other endpoint? Careful.
20?
20, 80, 40, what? So if s was 0, then we're getting all what?
Circles?
This is like all circle. At the other end, where we're all square, s would be 20, right? Because that we've only got 80 feet, we'd need 4 sides to actually make the square, so that would be 20, that's the other edge. We're going to check. So can you guys plug those into A of s? I erased it, but plug those in. Use your calculator. See what you get. Let's see which one gives us the minimum thing, because it might be one of these edges. I don't know. Looked pretty close. When we were doing it on the board, I mean, the area of the big circle versus like the square and the circle at that critical point, it was pretty close. I don't know.
What do we plug that
call.
into?
You're plugging it in, so look, it says right here. Remember
So,
we had A of S right underneath this guy? So it was, I'll put it back up if you want to do it. So we had that A of S was.
we had it as A of R.
Yeah.
You wrote it as A of R. I don't know. It was A of S, but it was just
Was it A of S or A of R? I forget, because I switched from what I did in my notes.
put A of R. Well, we did.
It was pi,
But it's
it was S.
Yeah.
Yeah, it was S. So didn't we solve for R, and R was 80,
80 minus 4S over 2
yes,
That was R.
there you go. So plug those three guys in. Okay. Plug those 3 candidates in and see which one gives you the actual minimum, because we're not sure. Did you change this password?
You changed my use password.
Actually, it's mine.
This password.
All right.
Thank you. Oh, and by the way, there were a lot smarter ways to do those too. And actually plugging in the function right there. If it's all square and that side is 20, then and if it's all circle, then I guess maybe not. We could go 2 pi r plus 80,000.
2,000? 509. Or 286.
That's what I have. That one. Couple ways you can do that though. Somebody have the other one for the critical point?
224.03. What's that 9 being? So 102.40. Yep.
They don't care if you truncate on the AP test, though. You could have said through 9. Wouldn't matter. Anyway, so the minimum did happen at the critical point. Seems like we're a little tired. I wanted to do one more example.
I'm down.
Should we wait a little bit, take a little break, or what? Should we just go for it? Okay, let's do one more. I know it's a long day, long week. I'm feeling it too. At least we're watching a movie next hour. Good movie. Bad. You can come watch our movie with us. It's the Emperor's Club.
Let's get moving.
Just tell Senora you got sick. I'm sure that'll go over real nice.
Yeah.
Okay, last one. So let's say we have 2 poles, all right? So I'm going to draw 2 poles. Let's say one's there, one's a little bit taller, so the poles are not the same size. Let's say this one is 6, and this one is 15. I'm going to give you some units, let's say feet. Okay, so we've got those 2 fixed constant poles, and we're trying to decide, we're going to string a length of wire. So we're going to string a length of wire down like this somewhere, kind of like we're making a tent or something, I don't know. So that's one piece of wire, and we're going to like stake it in somewhere. And our goal is to stake it in a place that makes us just so happy. Okay, there's a couple variations we could do on this problem, but I thought we'd do a different kind of function. So in this problem, we're going to say, where do we stake it so that the angle formed by the 2 pieces of wire is a maximum? So what do I mean by that? So let's think about it like this. We could also do it so that, where can we stake it so that that length of the wire is like minimum, or that length of the wire is maximum, so we use like the least amount of wire. Maybe this is like a superconductor or something, and it costs like, oh, I don't know, a couple $100,000 per foot to make, so it's pretty expensive wire. We don't want to waste any, you know what I'm saying? It could be a very realistic type of problem. So, but anyway, we're not going to think about the length, we're going to think about the angles, just so we can do a different kind of thing. So our goal here is, let's think about 3 angles, so we'll call this one theta, we'll call this one delta, I'm going to call this one phi.
What's delta?
I don't know, we're D. My deltas are always weird too, so they're probably not very good. But anyway, so let's write our goal up here. So where should the stake be placed? So in this visual, it's right here, but I mean, we could slide it back this way or slide it forward that way. Where should the stake be placed so the angle formed by the pieces is a maximum? Okay, so first of all, here's how we're going to do this. So first we're going to say, what's a constraint on our situation? Well, we've got like the 6 and the 15, but what else about this whole angle here? It equals 180, right? Like that you can't change. The ground is the ground, and we're going to pretend this ground is flat. So we're going to say delta plus theta plus phi equals, and we don't like to work in degrees, equals pi. So we're working in radians in calculus almost always, right? So we're going to say equals pi. So that's something that we need to know. What else can we do here? Well, we're mainly just interested in these two guys. So, the triangles.
Triangles, and then like the second leg is gonna be like if you think of the total length at the bottom as x, then you can relate the two second legs to each other. You know what I'm saying?
Yeah, I know what you're saying. Okay, so what's Jake saying? So one other piece of information that I didn't tell you is how far apart these poles are. The poles are 20 feet apart. So I mean, unless I told you how far they were apart, couldn't you just like move the poles and kind of like change what's happening? So these are like in a fixed location. They're a fixed height and they're a fixed location from one another. So now what Jake was saying was you should call something.
One leg, one side x, and the other one like 20 minus x.
So like from here to here is x, and that means wherever that is, because you can slide it, right? It's variable. That's why we called it x. So you can slide this around, but no matter what, this is going to be 20 minus x from there to there, isn't it? Does that make sense? So now once we have that labeled, what are we really trying to find here when we said, where should the stake be placed? We're trying to find what? The optimal location of x. We're trying to optimize what our x should be. So if we want to get an equation involving x now, let's just look at it. Can we do like a couple different ones? So like what? Tangent of this triangle equals
15 over 20 minus x.
that. There's one equation. And then we can do another one for the little triangle that says tangent of delta equals 6 over x. So those both involve x. Why are we using both of them though in this case?
So we can substitute.
Can we compare them? And maximum?
Well, that's a good idea. But aren't we?
Because you have three variables, sort of.
By the pieces really implies like both pieces. We're trying to get like the total of these two angles to be a maximum. That's what they really asked us. They didn't just ask us to maximize one of them. If they had, then we could just use one of those. They asked us for like the total of those two angles to be the most that we could make it. So we're going to do what with those two angles?
Put them in. The delta plus theta is
Okay.
Don't you want to minimize the sum of those two angles? So
Well,
that
I
you can
said-
maximize theta.
Minimize the sum. Well, the question is, what are they asking us to maximize? Let me see what
Was
they
it
said.
theta or
Let's see.
It's the equal form, but uses I think it's
I didn't look at this beforehand. I just found it look cool.
We want to minimize theta, right? So if the
Where should the wire be staked so that the angle formed by the two pieces of wire at the stake is a maximum?
Oh, so theta doesn't want to
Yeah, they're talking about theta, right? So they want this to be a maximum. So that implies, like Paul's saying, that these, the two pieces added up, are a minimum. So we should really solve for what in that thing?
theta.
Yeah, you guys were onto it. So theta equals what?
Pi minus delta minus e.
Okay. So do we have expressions for those things? Well, pi is pi.
we have the other ones if
Ah, and we have the other ones too, right? So delta is really,
Yeah, tangent to 6 over x.
and phi is really, yes. So that's a function. What's the variable in it? That's theta of x. So it's one variable. So we have to worry about our two variable thing. We need a secondary equation. No, we've got it. So then we're just going to do what with that thing?
Take derivative.
Take a derivative and figure it out.
This is a fun derivative.
Well, I don't think it's that bad. Arc functions aren't too bad. Let's see, maybe. So theta prime of x. All derivatives are easy. Come on. Okay, so what happens to pi? It's gone. And we've got negative 1 over, what's the inverse? What's the derivative of inverse tangent? 1 plus thing squared. Do we have a chain rule? You can see the inside has a function. What's another thing that we could call that? That could be called 6. So this is really multiplied by,
over x squared.
so there's that part. Then for the next part, we're going to have minus, let's just go like this, plus minus 1 over, okay, so on that one, we're going to have 1 plus thing squared times, what's the derivative of that thing? If we make this easy, we could say 15, 20 minus x to the negative 1, or we're going to have to use the quotient rule, right? What do you guys want to do? You want to do it that way or quotient rule?
No, that way.
Okay, let's go that way then. So then we're going to have negative 15, 20 minus x to the negative 2, and the derivative of that inside is negative 1. Oh, it did get pretty ugly. You guys are right.
It's not that bad.
So let's see.
6x.
So that's 6 over x squared 1 plus 36 over x squared minus 1 over, oh no, let's go. Minus is minus 15. 20 minus x squared, 1 plus 15, 20 minus x, squared there. Yuck. Anyway, I'm going to leave the simplifying to you. It's just a bunch of annoying algebra.
What would it be plus that? There's three negatives.
3 negatives is
Negative.
negative, isn't it?
Oh,
You
yeah.
have negative,
Odd.
positive,
I
positive.
even did it and it came out negative. I don't know.
Anyway, they simplified it. Only took like 2 more steps, but I'm not going to do them. So trust me, in 2 more steps, it simplifies down to something that looks like this.
Oh, it does simplify pretty nice though, so that squares go over there.
Yeah. So let's think about where that would be equal to 0, or where that would be undefined. The top would be equal to 0 at 2 possible places, wouldn't it? It's quadratic, unless it's imaginary. I mean, hopefully not. The bottom would be equal to 0 here at all. That's like plus or minus 6i, isn't it? That wouldn't be working. And this thing we don't know about until we would check it. So when they did the top, like in their quadratic formula or just using their graph, because do you think that the AP calculus test would give you something this ugly without a calculator? No way. No way they're going to do that. But anyway, so let's say we have a calculator, we graph this. Do you guys graph the top?
Something.
Ah, you got it?
9.785.
So the 2 zeros at the top, I want more space. Trying to get it in the video. So x equals about 9 point, what's the one I have here? 7847.
And the other one is a negative number, so
Negative 36.
The other one's like way that way. When you graph this parabola, it ends up looking like this. Here's the 9, and then the other one's way over there. So it doesn't matter, right? Like that's something that doesn't physically make sense because of back in our diagram, you can't make x be negative this way. That doesn't make sense. So the answer was 9.7847. So you want to describe that, how would you say your final answer? You'd say like, to achieve the maximum angle here, to make that the biggest, the widest, I'm going to place my stake for this wire 9.7847 feet from the left-hand side. Does that make sense? So I thought we'd just do a different one with different functions. All right. Hope you found that interesting. Was an ugly algebra thing.